Hello, students. We're talking about volume of pyramids and cones. So these are all what? These are all pyramids. And what are pyramids? What kinds of pyramids are these? This one is the normal looking one. This one is a square pyramid, or if we didn't know that the base was a square, we could call it a rectangular pyramid. What about this one? What's the shape of this base? A triangular pyramid. This happens to look like a tetrahedron if all of these triangles are the same. The angle and the rotation sometimes makes it hard to see that. What do we think this one is? We had this one the other day. Good. It's a pentagonal prism. What about this one? So, sorry, not a prism, it's a pyramid. I'm tired. Pyramid. Okay, so we got all these pyramids. What makes something a pyramid, and what are some vocabulary words that go with it? So a pyramid is a polyhedron. Basically, that means a three-dimensional shape made of polygons for the faces with one base going to a point. That's not the best definition. I'm sure we could find a better one in the book. The point is what makes something a pyramid. So the point is kind of what's interesting here. This point up here, see how they're all going to a point? That point has a special name. That point is called the apex. The apex is the top point of a pyramid. And unlike prisms, pyramids have only one base. So what shape is the base of this one? Well, it's a trapezoid. So this is a trapezoidal prism pyramid. I don't know why I keep saying prism. Pyramid. What's different about this one? This one looks a little different, right? First of all, we could look at the base. The base looks like a regular hexagon, but it's kind of tilted. Do you remember what we call it when it's tilted? It's an oblique hexagonal pyramid. Those are, oh, there's one other thing. So if you look at the bases are sort of a different shape. What are the other faces? What shape are these? Are these lateral faces? The lateral faces, that means the ones that aren't the base, are triangles. In all the pyramids, it's made up of a bunch of triangles with a different shaped base. Unless it's a triangular pyramid, then they're all triangles. But here, if I showed you the net, this would look like we would have a square in the middle, and then these triangle, flaps would kind of fold up together. Kind of cut off here. Let me move that guy. Move over here, you oblique hexagonal. And I put lots of fun links for you to look at. This is called a net. And again, you can see that the base is a different shape than the lateral faces. And if it's a perfect square pyramid, then all of these would fold up to that apex point, and all four of these would be congruent. We could try to find the surface area. This triangle is like a different size and shape than this triangle. But if this is a isosceles trapezoid, these two triangles would be the same. So it kind of depends if it's a regular figure on the bottom, then all the trapezoids, all the triangles will be the same. If it's not regular, then the triangles will be different sizes. So that's how pyramids work. The volume of a pyramid is 1/3 the product of the area of the base times the height of the pyramid. So it's the same formula, base area times height, as we had for prisms, but there's this 1/3 right here, which is kind of interesting. I'm going to show you a video. So this is a video demonstrating why the volume of a pyramid is 1/3. Here we have two different bases on two different solids. One's a triangular, one's a square pyramid, one is a cube. And they have the same height. Fill the square pyramid with liquid and see how the volume compares. So what did that show? A little abrupt there, but what did that show? It showed that 3 of those fit inside of one of the cubes. So if we're going to do these problems, it's not hard. We just have to say, oh, look, it's a pyramid. So instead of doing volume is length times width times height, which is what you might have thought in elementary and middle school, volume is not length times width times height. For rectangular prisms, it is, but for other shapes, it's sometimes more complicated. So the volume of this pyramid right here is 1/3 the base area times the height. And the height of the pyramid, I'm going to do that first. I think I'm going to do the base area off to the side. The height of the pyramid is the distance from the base to the apex. It's that perpendicular distance. Sometimes they draw it inside. So the height of this pyramid is 6 centimeters. And then the base area, maybe I'll do it here. It's the, okay, the base is a rectangle. And it's a rectangle that is 9 centimeters by 7 centimeters. So if I want to find the area of the base, I want to know how many squares would fit in here. And that's just going to be 9 times 7, which is 63. I'm going to put that up here. I kind of showed my work by drawing the picture. So we have 63 centimeters squared times 6 centimeters times 1/3. I'm going to do 1/3 of 63, which is going to be 21 centimeters squared. And then I'll multiply that by 6. For me, that was easier to do in my head. So that's going to be 126. And we do centimeters times centimeters. And then times centimeters is going to be centimeters cubed. So the volume of that pyramid right there is 126 centimeters cube. Sometimes we say cubic centimeters. Hey, look, this is also a pyramid. It has one triangle that's different than the other 3. So that's going to be the base. And this is the apex. So I see a pyramid right here. I just learned that the volume for a pyramid is 1/3 the base area times the height. The area of the base, or the base area, Well, what's the base of this? The base of this is a triangle that looks like that. Okay, and I'm going to bring the measurements with it. It is 7.5 centimeters along the base of the base. The base of the base, little base, and so we have the base of the pyramid, and then we have the base of the base. And so what shape is the base? Well, it's a triangle, and we know the area of a triangle is half the little base times the little height. The height of the pyramid is 10. It's 10 to get from the base up to the apex, 10 centimeters. The base area is going to be whatever the area of this triangle is. So this triangle has a little base, little b, of 7.5. And what's the height of the triangle? The height of the triangle is 8 centimeters. So the area of the base, or the base area, is 7.5 centimeters times 8 centimeters. Half of that. So that's going to be, I'm going to do half of 8, which is 4. And then on my calculator, I'm going to do 4 times 7.5, which is 30. 30 centimeters squared. So it takes 30 centimeters squares to cover this. And then we have a height of 10. Oh, they're so nice to us. What's a third of 30? That's just 10. So 10 squares times 10 centimeters is 100 cubic centimeters. Ooh, a little messy, but not too bad. Ooh, what's different about this one? We already talked about it. It's oblique. So the question is, does Cavallari's principle hold for this one? I'm going to open up another link. Okay, let's take a look at this. So what do we have here? We have a pyramid. It looks like a lovely square pyramid. We can look at the cross section. So as it gets closer to the top, the area of the cross section is getting smaller. So all of these areas are the same. Question is, if I make this oblique, if I wiggle that over, are the cross sections also going to be the same? Even if it's oblique, am I going to have the same cross section? Yep, even if I tilt it way over, all of these cross sections are going to be the area of all the cross sections, it's going to be the same. So what does that prove? That proves that it doesn't matter if it's oblique. So Cavallari's principle, it does hold true for pyramids. Every level of a right, where the apex is right above at a right angle, is going to be the same as the oblique pyramids. If the cross-sectional areas are the same, then the volumes are going to be equal. Okay, so this is our hexagonal oblique pyramid, and we're not going to worry about it being oblique, and we're just going to do this problem. So we know that the volume of the pyramid is a third of the base area times the height. The hardest part about this problem is that we kind of skipped the section where we learned how to find the area of regular polygons. So the height's not hard to see. The height is that perpendicular distance between from this base up to the apex. The thing that's really fun on this one is trying to figure out what the area of this hexagon is. And you probably do not know the formula for the area of a hexagon. You might be able to look it up. Okay, so we need to find the area of the base. And we know that the base is a hexagon. And there's lines on all the sides, which is helpful. This is a regular hexagon. All of the sides on this hexagon are 2 meters. Okay, I don't know how to find the area of a hexagon. I do, but you guys probably don't. So let me show you one way to think about it. What shapes do we know how to find the area of? We know how to find the area of triangles, right? So if I could find the area of this triangle and I multiplied it by 6, that would give me the area of the hexagon because there's 6 of these sides triangles in there. So I don't know what it is yet. I'm looking for it. I'm going to play with it. The area of the base is whatever the area of this hexagon is. And I know that it's 6 triangles. But now I need to focus in on that triangle. So what do we know about that triangle? We know it has a base of 2. Can we find the height of the triangle? I don't know, but we're going to need it if we want to find it. Okay, so we need to find that because if I had that, then I could do area of a triangle is half the base times the height. I know the base of this triangle is 2. So that's interesting. 2 meters. Oh, sorry, I put that in the wrong spot. I need to know the height of the triangle. So how are we going to find the height of this triangle? Well, for that, we're going to have to go back and say, wait a minute. Let's see if we can figure out some of the angles here. So this angle would be interesting to know. And I can find that angle because all 6 of these triangles are the same because this is a regular hexagon. So what is 1, 2, 3, 4, 5, 360 all the way around divided by 6? 60. Guess what? This angle at the top is 60 and we split it into half, which means it's both 30. Which means this is 60. Hello. Do you recognize a 30, 60, 90? That should be familiar. That I did not skip. Okay, this is a 30, 60, 90 right triangle. This 30 tells me that this is half. So this is 1 meter in this 30, 60, 90. And this is going to be 2 meters. These are all going to be equilateral triangles in here. Everything's going to be 2, 2, 2, 2, 2, 2, 2, 2. But how long is it going to be down the middle? The height of this triangle is going to be 1 times the square root of 3 meters. Don't know that. You can keep practicing your special right triangle work because that stuff doesn't go away and it shows up in all the most random of problems. So guess what? The area of this triangle is the square root of 3 meters squared. The area of this triangle is the square root of 3 meters squared. How many of them do we have? We have 6. So the base area is going to be 6 times the area of the triangle. So we know it's going to be 6 times the square root of 3 meters squared. So I'm going to put that here. We got 6 times the square root of 3 meters squared. They're so nice to us. What's a third of 6? 2. And 2 times 5 is 10. So this is going to be 10 square root 3 meters cubed. That was fun. This is the volume. Volume of the hexagonal oblique pyramid is 10 square root of 3. Again, we put our regular numbers in front, then our irrational numbers, and then our units. That's the best way to write the answer. If you were actually building something or making something and you needed to know how much material you needed, you could plug that into a calculator and write the decimal. Hey, do we remember what happens when we spin a isosceles triangle around a vertical line? We get a cone. These are all cones. This point is still called the apex. What measurements do we have on cones? We have the height. Here's an oblique cone. So cones can be oblique. They also have a base, but the base on all of them is a circle. This one's kind of a composite, but I thought it was cool, so I put it there. Ice cream. So it's like a pyramid in that it's, you know, has a chunk missing. If I drew the rest of the cylinder with the same height, you could see if I try to fill in the cylinder and fill in the cone, it would be a lot more space in the cylinder. So the cone is actually 1/3 of the volume of the cylinder. And we know that all the bases of cylinders and cones are circles, so we can replace the base area with pi r squared. So let's practice. So we got the volume of a cone it's not length times width times height. It's not base area times height because there's a chunk missing. There's these pieces missing. So it's 1/3 of, and you can write pi r squared h if you want to memorize that way. It's 1/3 the base area times the height. The height of this cone is 18 inches. What's the radius of this cone? Careful, it's not 11, is it? Radius is from the center of the circle to a point on the circle. So I could go out maybe to there. I need I need the radius, not the all the way across. So they gave us the diameter. We want the radius. So we have to do a little bit of work on this one. This is really the only way that I could trick you is to give you the diameter instead of the radius. And the radius is just half. So I'm just going to do 11 divided by 2, and that's going to be 5.5. And that is inches. All right, now for this one, I think I'm going to use the calculator. And yeah, because I'm already squaring this. So let's just be slightly lazy and type some stuff into a Desmos calculator. It's the scientific calculator, and I'm going to do 1/3 like that, and I'm going to multiply by parentheses 5.5 quantity squared. Now you can't put units in here because it'll confuse it. It won't know what you want. Times 18. Did I do it right? Oh, I need pi. Okay, so this would be 181.5 pi if you wanted to do it that way. 181.5 pi. And then inches times inches is inches squared times inches is inches cubed. You could put it like that. Or we could put pi in there and we could get our approximate answer, which is like a pi button, boom, 570.2-ish. Interesting. Let's see. Ooh, do you think it works for cones? It does. Doesn't matter if it's tilted. So we would do this the same way. So the volume of the cone doesn't matter that it's oblique. If they were really being mean, they might give us a lateral edge and try to make sure we knew that we wanted, you know, this number and not whatever. Maybe this was like 8.4 or something. That would be just there to confuse us and trick us. You might need that measurement if you're doing surface area, but you don't need it for volume. So the volume of the cone is 1/3 pi r squared h. And what's the radius on this one? The radius on this one, oops, I did that wrong. The radius on this one is 3. They're making it so nice on us. 3 centimeters squared times 7 centimeters. How do I know they're making it nice? Because they're choosing multiples of 3 here. So this is 9 centimeters squared divided by 3 is 3 centimeters squared. 3 centimeters squared times 7 centimeters is 21. 3 times 7 is 21 pi centimeters cubed. So that's 1/3 of 9. This is 9 centimeters squared. I'm not showing that very well, but okay. And then I did 1/3 of 9 is 3, and 3 times 7 is 21. Again, number, irrational number, and then units. Ooh, these are extra fun. Composites. So if I want to find the volume of all of it, I'm going to do the volume of the rectangular prism. And then on top of that, I'm going to add the volume of the pyramid. These are fun. You just have to kind of stick with it. The volume of the composite solid. So the prism is going to be base area times height. So that's going to be base area times height. And then the volume of the pyramid is going to be 1/3. It has the same base area, but it's a different height. It's the height of the pyramid. So if the whole thing is 24, how much is the height stopping right here? How much is it from the apex here to right there? Well, one way to look at that is the whole thing's 24 and this part of it's 11. So if we do 24 minus 11, we get what? 13? Yeah. Okay. So this height and this height are different. These base areas are the same. So the volume of the composite is going to be the base area times the height. I'm going to do base area off to the side because I don't want to get confused. Wow, that's really strangely drawn. So I'm going to do 12 times 18 off to the side. 12 times 18 is 216 feet squared fit in the base. So I'm going to do 216 feet squared times 11 feet. That's the height of the prism. And I'm going to do 1/3 of 216 feet squared times 13 feet. Oh boy, running out of room. And all of this is just calculation. So if divisible by 3, it is, wow, they're so nice to us. So the volume of the composite, I just did 216 divided by 3, and that was 72. 72 feet squared times 13 feet. And then I'm going to do 216 times 11, which is 2,376 feet cubed. So more than 2,000 feet cubes fit in here. And then another 72 times 13. Another 936 fit in the top. Another 936 cubes fit in the top. So the final answer here is if we add 2,376 cubes plus 936 cubes, we get 2,376 plus 936. The final answer is 3,312 lovely feet cubes will fit in this shape. This one's fun too. What's the volume of the part, the cylinder with the cone cut out of it? And this is the same type of problem, except you're subtracting the volumes. So we're going to do the volume of the, I don't even know what to call it. It would be like the space between the cone and the cylinder. Maybe I'll say the space is equal to the volume of the cylinder minus the volume of the cone. And the volume of the space in between them is going to be pi r squared h minus 1/3 pi r squared h. Now the h in both of these is the same, but the radii are different. The radius of the cylinder is 8. The radius of the cone is how much? Careful, it's not 4, it's 2 inches is the radius because it's half of the diameter. So the volume of the space in between those two shapes is pi, this is the cylinder, 8 inches squared times 9 inches minus 1/3 pi. R squared for this was the 2 inches squared. And the height of the cone is also 9 inches. Cool. Look, see, they put 9 in there for us. What's 1/3 of 9? That's 3 inches. What did I do wrong? Oh, I forgot to square that. Okay. So that's 3 inches if I do 1/3 of 9. And then I have times pi. And then what's 2 inches times 2 inches? That's 4 inches squared. And let's come back to the cylinder. The volume of the space in between. This is going to be 8 squared is 64. So I'm going to do this on a calculator. 64 times 9. 576 pi inches cubed. So the volume of the space in between them is 576 pi inches cubed minus 12 pi inches cubed. So to finish this, I do 576 minus 12. And they both have pi inches cubed, so I can combine those. Okay, so the volume of the space is 564 pi inches cubed. If I find a mistake, put it in the comments. Sorry, if you find one of my mistakes, please put it in the comments. All right, be good, keep working. We're getting there. Keep learning. Bye.